Morning, everyone. Able to hear me? Okay, so right. All right. So today we'll do spring force, right? How does a spring behave, and how to tackle problems involving springs. All right. Let's understand spring force first. We were dealing with strings, which were inextensible strings. There are three kinds. One is inextensible string. The other is extensible string. Inextensible. The other is string. The other is extensible string. All right. So we have dealt with inextensible strings, which do not extend. All right. Length of the string remains constant. Now we will deal with strings, then later we'll deal with extensible strings. Now let's talk about what a string is. String is something which will not just even pull, but also push. String has got a structure something like this: a coil, helical structure. If I've got a mass attached to the spring, if I say natural length of the string is L naught, what is observed in experiments is if I displace the block by x, string force is proportional to x and opposite to the direction of extension. If the spring is extended by x, spring pulls the block backward by a force which is proportional to x. If the block is moved towards left, that means if the spring is compressed, then the spring force is towards right and proportional to x. That's compression. So spring force is observed to be proportional to compression or extension and oppositely directed to the extension or compression. If I remove this proportionality sign, I'll get a proportionality constant, which is k naught, which is called spring constant of the spring. So spring force is given by F is equal to minus k naught x. Vectorially, F bar is equal to minus k naught x bar. That means if x bar is towards right, directed towards right, spring force is directed towards left because negative of x bar. If displacement is towards left, if x bar is towards left, then spring force is negative of x bar, which is towards right. All right. This is what you have to understand carefully. That means if I extend the spring, spring pulls back. If I compress the spring pushes it. So spring can do both. It can pull and push. Whereas a string, if I have a block and a string, if I pull this one, string will pull it back. But if I push it towards left, push the block towards left, my string will slacken and there is no force in the string. Tension becomes zero. But whereas in a spring, tension is proportional to x and oppositely directed to the displacement vector from the equilibrium position, from the natural length position. If natural length is L naught, if displacement is x towards right, spring pulls it towards left. If the spring force is towards displacement is towards left, spring force is towards right. Graphically, spring force is elongation x, elongation or compression. passes through origin. That means if it is natural length, spring force is 0. If the extension is x, spring force is minus kx. Slope of this line is minus k naught. If there is a compression, that means my displacement is negative. That's compression. This is compression, this is elongation. If there is compression, elongation or extension in the spring. So if this is elongation, spring force is towards left. If there is a compression, spring force is towards right. All right. Now look at the students. If I displace the particle by x naught and leave it, what happens? Force is towards left. So particle is at rest. Force is towards left. So that force will decide in which direction the particle will start moving. So particle will start moving towards left, right? If it is displaced towards right, and I leave it, it's at rest. Force is towards left. So particle will start moving towards left. Because of which, because of the force, it will start accelerating towards left. As it reaches origin, natural length position. All right, natural length position is the origin. As it reaches origin, it accelerates, speeds up. Its force is decreasing, but its speed is increasing because force is decreased, but force is still in the same direction as velocity. Acceleration and velocity are in the same direction. That means particle speeds up, goes on speeding up. All right. So when it reaches origin, net force becomes 0, but it will have acquired some velocity v naught, because of which it will overshoot. I displace it till the extent of x naught. It accelerated. When it reaches natural in position, it will acquire some velocity, because of which it will overshoot. When it overshoots, let's say it reaches this position where the force is towards right, but the velocity is towards left. That means acceleration is towards right, velocity is towards left. That means the particle is retarding. So it slows down. It will stop symmetrically with respect to origin, because graph is symmetric with respect to origin. It's a odd function. It's a point symmetric function with the point of symmetry as origin. So it is symmetric with respect to the point of symmetry. So motion is symmetric with respect to the point of symmetry of the graph. We have done such graph in AX graphs. All right, if you remember, we have done AX graph is just same as AX graph, except that if I divide by mass over here, I'll get acceleration. So I'll get the AX graph, which is of same structure, linear graph. And we have done linear graphs, AX graph. We have done 2 kinds of AX graphs in detail. This is one, this is one. And we have drawn phase portrait for this one, and we haven't done for this one phase portrait. We thought we'll draw it after you learn hyperbola, after I teach you what a hyperbola is. So this is to be done later, but this is what we have done. But graphical analysis and physical analysis of both the situations we have done. AX graphs, this is A, X, A, X. Now look at this. This is the same structure as this one, except that if I divide by mass, I'll get the acceleration. Or if I multiply by mass over here, I'll get the force. So graphical analysis is the same. How do I do it? If I displace the particle by x naught, I see what the force on it is. Force is towards left or right. If it's towards left, particle will start moving towards left, because of which it will start speeding up. It will acquire some velocity when it reaches origin. It will overshoot. And the particle stops symmetrically with respect to point of symmetry, which is origin. All right. Now there will be cases when this graph is not symmetric. All right, the graph is something like this. It's broken here. It's fractured here. All right, in those cases, what happens, we'll deal with such cases later, but there will be cases where this is not symmetric. But here it is symmetric. It is symmetric because we are dealing with the same spring, only one spring. Here you'll have cases when you have got multiple springs. But right now, let us deal only with a spring case where you have got one spring of natural length L naught, spring constant K naught, equilibrium position as origin, and displacement is X naught or X. Whether if it is towards right, force is towards left. If the displacement is towards left, force is towards right. All right, this is what the scenario is. But now, let us understand. I've got a spring. This is a block. Natural length of the spring is L naught. So initially the block is at spring is at natural length. Spring constant is K naught. If I displace it, not displace it. If I apply a force of F naught, let us say the position is at X naught, displacement is X naught, and the force is F naught. And it's found that particle is in equilibrium. So what is the relation between X naught and F naught? I draw the FBD of the block, normal reaction upwards, mass is M, so mg downwards. This force is towards right, spring force is towards left, which is K naught X naught. Because it's in equilibrium, I said net force on that is zero. Net force in vertical direction, net force in horizontal direction is zero. Net force in vertical direction means N minus mg is equal to zero. So N is equal to mg. In horizontal direction, I've got F minus K naught X naught equal to zero. So X naught equilibrium extension is F by F naught by K naught. That's the equilibrium extension. All right. So how do I find the extension in the spring? I find the net force on the block equated to the spring force. Spring force is nothing but K naught times extension or compression in the spring. I equate this to 0. Net force is equal to 0. Net force is this minus of this is equal to 0. Mass into
Sir,
acceleration. Acceleration is 0. As I said, it's an equilibrium. So x naught is equal to F naught by K naught.
sir,
Yes.
I think X naught equal to K naught by F.
How? Now look at this. This goes on towards right. F naught is equal to K naught X naught. K naught comes in the denominator. F naught by K naught.
Ah, right, sir. Okay.
ठीक है ना?
Yes.
हाँ. Good that you're following. Right. Now, look at this, students. K naught is equal to F naught by X naught. All right. So units of K naught would be Newton per meter. Right. So units would be some number. Let's say 200 Newton per meter are the units of the K naught, spring constant K. All right. What is dimensions? We'll look into dimensions later. But right now, what are the units of F? Newton. Units of displacement is meter. So units of K is spring constant is Newton per meter. All right. Now let us say I've got a K is equal to 200. Asa, intuitively, if it is difficult for me to pull the string, then string is stiffer. More is the K naught, more is the stiffness of the string. It's called stiffness constant or spring constant. The spring constant is also known as stiffness constant or stiffness of the spring. More is K naught, more is the stiffness of the spring. Intuitively, what it means is it is difficult for me to stretch the spring or compress the spring. If it is very easy to stretch the string, then K is less, K naught is less. If there are two springs in which one spring is, it's easier for me to stretch one spring, and it's difficult for me to stretch the other spring. The one which is easier has got less K naught compared to the one which is difficult to stretch. Difficult to stretch. All right. So easier to stretch, lesser is K naught. Difficult to stretch, more is K naught. So if I've got two springs, K is equal to 100 and K is equal to 200 Newton per meter, 100 Newton per meter and 200 Newton per meter. Which do you think is easy to handle, easy to stretch? 100. All right. K naught is equal to 100. It's easier to stretch because K naught is less. Intuitively, that is what it means. If you, let's say, if I give you two springs and tell you which one is more stiffer, which has got more stiffness constant, you just pull the string and see. Pull both the springs, whichever is relatively tougher to stretch, that has got more K naught, and the which has got relatively easier to stretch, that's got less K naught. All right. Okay. Now I've got mass is m naught. I apply a force of 400 Newton. I have to find the extension in the spring. How do I do it? I draw the FBD. Any Newton's laws problem starts with an FBD. In fact, starts with a reference frame. You choose a reference frame. I'm choosing ground as a reference frame. I draw the FBD of the spring, FBD of the block, and write F is equal to ma. If acceleration is zero, net force is zero. All right, particle is in equilibrium. So,
Sir,
yes,
can you make the screen clear, sir? On camera.
is it blurred?
Yeah, sir.
Hmm. Is it still blurred? And one second, let me just put it on spotlight. Yeah, is it still blurred, Vignesh?
No, sir. Now it's clear, sir.
It's clear? All right. All right. So I draw the FBD of the block. This is 400. This is K naught into X, where X is the extension in the string. So 200 into X is equal to 400. So X is equal to 2 meters. That's very huge. All right. Usually you'll have 20 20 Newton per meter or something like that. And that's very huge. 2 meters is very huge. One more thing, students. Strings have got a linear variation. F is equal to minus K naught X. And this is known as Hooke's law because it was discovered by Sir Robert Hooke. And springs which obey this Hooke's law are called Hookean springs. Usually, springs have got linear function, but there are springs with a nonlinear function as well. That means if I stretch too much, then it's not going to be proportional to x. All right, springs which behave with linear fashion with f proportional to x minus x, then such springs are called Hookean springs or linear springs. But there will be nonlinear springs as well. Nonlinear where f is not proportional to x but x minus x square or something like that, quadratic or some cubic function. All right, there are springs as such as well. That's practical. These are ideal cases where I can approximate any spring to linear function. Mass is 2 kg or mass is m naught. Spring constant is k naught. It's vertically hung. G bar is downward. Okay, now I have to find the equilibrium extension in the string. What do I do? I leave this block in equilibrium position. Let the extension be x naught. I draw the FBD of the block. K naught into x naught, and this is mg, m naught g. So x naught is k naught x naught minus mg equal to 0. So x naught is equal to m naught g by k naught. That's my extension, equilibrium extension of the string. All right.
Yes, sir.
Now let us say the same thing is in a lift, which is going upward with an acceleration a. Now, what is the equilibrium extension in the spring is what I have to find out. Now, what happens with respect to ground, the particle is accelerating upwards, but with respect to the lift, it's in equilibrium because there is a pseudo force field now. I've got a mg field, gravitational field as such as usual, but I've got a pseudo force field as well. I talked about pseudo force field last time, where I have ma naught downward at every point because it is opposite. Pseudo force is opposite to the direction of acceleration of the reference frame and equal to mass into acceleration of the reference frame. So pseudo force on the block is, now if I draw the FBD of, I choose a reference frame first, right? I'll choose a reference frame as ground. With respect to ground, let us write the equations. Then with respect to the lift, let us write the same equations, and let's get the equilibrium extension in both the cases. So at equilibrium, let the extension be x naught. So spring force is kx naught. This is m naught g. Acceleration is a naught upwards. So I've got FBD and MAD both. All I have to do is write the equation. F is equal to mass into acceleration. So what is F? A naught x naught minus m naught g is equal to m naught into a naught. So x naught is equal to m naught into g plus a by k naught, where I can write this as m into g effective by k naught, m naught into g effective gx by k naught. All right, that's what I got. And look at this equation, students. This is net force is equal to mass into acceleration because the particle is accelerating over here. If I draw the same FVD, choosing a reference frame as my lift, how will I get it? I'll do it here. I'll just do it here. K naught x naught, real forces will remain the same. M naught g. Now there is no acceleration. So MAD involves no acceleration. Acceleration is zero. But there's a pseudo force, which is M naught into A naught. Downward. Why is it downward? Because acceleration is upward. Acceleration of the reference frame is upward. Pseudo force is opposite to the direction of the acceleration of the reference frame. So its M naught is downward. Asha, reaction of mg is on earth. Reaction of k naught x naught is on spring. Reaction of m naught is, where is the reaction of m naught, students? I told you, whenever you think of a force, think of a reaction force as well immediately. That's a good habit. Now tell me, where is the reaction force of m naught, of the pseudo force?
Spring downward.
Uh-huh. No, I told you before, pseudo force does not have a reaction. Okay, it's just a mathematical term added to the equation so as to satisfy the Newton's laws of equations. All right, so as to make us comfortable in applying, that gives us license to apply Newton's laws of equation to a body in an accelerated reference frame, in a non-inertial reference frame. All right, so pseudo force does not have a reaction force. That is why it's called a pseudo force. It's a false force. Every real force will have an action-reaction pair, but a pseudo force will not have an action-reaction pair. Remember this, students. It's a very important point. All right, I told this to you before as well, but remember now, it's going to be, it will not have action-reaction pair. All right, let's write the equations now. Now there is no acceleration, so I'll write k naught x naught minus m a naught plus m naught a naught plus m naught g equal to 0. Look at this, students. These two equations are mathematically equivalent, mathematically same actually. But this means different and this means different. This means it's in equilibrium. This means particle is accelerating. It's not in equilibrium. All right, net force is resulting in mass into net force is resulting in acceleration, but here net force is 0. That's why acceleration is 0. So I'll have x naught is equal to m naught into a naught plus g by k naught. I get the same extension whether I choose reference frame as ground or reference frame as lift. I'll get the same extension. But choosing reference frame as left is comfortable and easier if you get by experience, you will find out that it's easy to do it, easy to crack a problem, easy to attack a problem from the reference frame of a left from a non-initial reference frame, applying pseudo force. This will be a little difficult. You will see in this case it was pretty simple in both the cases, but there will be cases where this is difficult and that's easier. Okay, we'll look into such cases later. But right now, you understand that any problem can be solved using either a ground frame or a lift frame, inertial frame or a non-inertial frame. But non-inertial frame becomes easier, as we'll see in future. But both equations will result in the same answer, but the equations will mean different. Here, equation means net force is resulting in acceleration. Here, equation means net force is zero, so acceleration is zero. It's in equilibrium here. It's not in equilibrium here. All right. Now, I wanted to do one thing. Now, let us say this lift, instead of accelerating upwards, is accelerating downwards in acceleration A naught. Now, what is the equilibrium extension in the spring?
K naught X naught plus M naught A naught
Yeah,
minus
what's your reference frame, Vignesh? Which reference frame have you chosen?
lift reference.
Okay. All right. And then go ahead.
1 minute. G minus. So X naught equal to M naught into G minus A by K naught.
Perfect. That's absolutely right. So you'll have, so G effective is now G minus A naught by K naught. So X naught is equal to M naught into G effective by K naught. Now my G effective is nothing but G minus A, right? My pseudo force field is upward. The acceleration field is upward A naught. So net acceleration is, effective acceleration is G minus A. So I'll have G minus A by K naught. And pseudo force in this case would be directed upwards because acceleration of the reference frame is downwards. Pseudo force is directed upwards. So M naught plus Kx naught is equal to mg. So Kx naught is equal to mg minus Ma naught. So G minus A naught. Right? That's perfect. It's good, Vignesh. I hope others are also understanding.
Yes, sir.
Okay, good. Now let's look at one thing. Now, if this were to move with an acceleration g, what would be the equilibrium extension then? Zero. That means my natural length is my equilibrium extension. Equilibrium position, sorry. So natural length itself is my equilibrium position. It is same as horizontal ground, horizontal plane. Horizontal plane ఉన్నప్పుడు natural length position is equilibrium position. All right, when this is G bar like this. All right, that's my equilibrium position. When this goes with G, my equilibrium position shifts to natural length position. So this problem is same as the horizontal plane. All right, because G minus A is zero. Students, don't experiment, please. All right. Now let's do a problem. All right, so how do I find the extension in the spring? I'll find tension in the spring by K naught will give me extension in the spring. All right, where F is tension in the spring, or T by K naught is my extension in the spring. Now let's say I've got a block, or before that, This is a 2 kg block, and it's 2 Newton per meter. K naught is 2 Newton per meter. I have to find the extension in the spring, equilibrium extension in the spring. How do I do it? Nothing. I choose a reference frame, which is ground. There's no accelerated reference frame here. I draw the FBD of the particle block, tension T, 2G, acceleration is 0, so MAD is complete, FBD is complete. So T is equal to T minus 2G equal to 0, T equal to 2G. So K naught X naught is equal to 2G, X naught is equal to 20 by 2, which is 10. Let us say this is 200. K naught is 200. All right, it's pretty stiff string. Otherwise, that will get elongated too much. That's impractical. So X naught is 2G by 200, which is 20 by 200, which is 0.1 meters or 10 centimeters. Check if it's correct. I could be wrong in this. Yeah, 20 by 200 is 1 by 10. 1 by 10 is 0.1 meter. Yeah. All right. So that's fine. Now, but then instead of this, only one spring, I mean, only one block, I've got a block like this, 2 kg and 2 kg. Now, what's the extension in the spring? For extension in the spring, I need tension in the spring. What is tension? Now, this 2 kg and this 2 kg, they are in equilibrium. So 2 kg is 20 kg, T minus 20 kg is 20, so T is 20. If T is 20, 20 by K naught is my extension in the spring, equilibrium extension in the spring, or reading of a spring balance. Spring balance is represented like this with a box and a spring. It reads, it will give me the extension of the spring. Spring balance reads, okay, how does, we'll come to spring balance later, but let's see what is the equilibrium extension in the spring? 20 by K naught, which is 0.1. 0.1 meter is a extension in the spring. But then if it is not 20, let's say, it is 10 and 20. That's 1 kg and 2 kg. In that case, what will the extension in the spring be? Ultimately, I want tension in the spring for extension in the spring. So how will I get tension in the spring now? To get the tension in the spring, I need acceleration of these blocks. If this goes up, that goes down. All right. So if that is the
10 by
case, if
K.
this goes, sorry,
10 by K, sir.
sorry,
10 by K.
what is that you're saying? Acceleration.
Mm, yes, sir.
Yeah, what is the
Close to
acceleration? 2g minus 1g by 3. So g by 3 is the acceleration, right? It's a look and say. Acceleration is look and say. G by 3. Now, once I get acceleration, I'll draw a video of one of the blocks. Let's say I'm drawing a video of 1 kg block. So T, 1g, and acceleration is g by 3. So I'll write T minus 1g is equal to 1 into g by 3. So T is equal to 4g by 3, 40 by 3. All right, let's say g is 10 for convenience, approximate value. T is 4g by 3. So extension in the string will be 4g by 3 by k naught, which is 4g by 3 k naught. That is 40 by 3 into 200, 1 by 15th of a meter. All right. So there's a difference between extension in the spring before and in this case, because the masses are different now. Particles are accelerating. And what is the acceleration of the particles? 2g minus 1g, supporting force minus opposing force by total mass. So g by 3. I get g by 3 is acceleration. I draw the FBD.
So
Yes,
here for 2 kg you have taken 20 g.
2g I've taken. But I've
2g.
drawn the FBD of 1 kg block. See. Yeah, Vignesh, what's your doubt?
సో మీకు ఇక్కడ 2 kg దగ్గర 20g minus 10g by
20g కాదు 20g కాదు 2g minus g 2g 2 kg block కదా
yes sir.
mg so 2g minus 1g
సో మరి ఇప్పుడు 4g దగ్గర 40 ఎందుకు ఇస్తున్నారు?
g ప్లేస్ లో 10 వేసాను
ఓకే సార్.
alright
ఓకే రైట్.
okay now this is 1 kg I have to find the equilibrium extension in the spring alright in terms of k naught itself let's say k naught I have to find the equilibrium extension of the spring. How do I do it? What is the acceleration of the blocks? Tell me. If this is a naught, that's also a naught. Yeah. So what is the acceleration of the blocks? Students, can you do me a favor? Can you revise that acceleration AX graphs and come back tomorrow? All right, revise AX graph, visualization of AX graph, so that we'll do a graph tomorrow related to spring, which is again an AX graph, I mean linear graph. We have done linear graphs already. AX has linear graph we have done. A is equal to kx we have done, A is equal to minus kx we have done, or specifically A is equal to minus x and A is equal to x we have done. All right. So please do me a favor, revise AX graph and come back tomorrow so that we'll have easy time for us to discuss the graphs in strings. All right. Okay. Tell me what is the acceleration of the blocks? It's a look and say. Students,
So is it g by 3?
now what is your supporting force?
Sir, it's sorry 2g by 3.
2g by 3, right? Yeah, it's a look and say. You should be quick in this. All right, students, others,
Yes, sir.
it's 2g by 3. You're convinced, right?
Yes, sir.
All right. Now I have to find the extension in the string. For that I need tension in the string. For tension, I can choose any one block. You choose one block. We'll draw the FBD of the block. Which block should I choose? 1 kg or 2 kg?
1 kg sir.
Because 1 kg is easier, right? You have got only tension in that.
Yes sir.
Tension, normal reaction, 1g. Normal reaction is counterbalanced by 1g. The only force which is responsible for the horizontal motion is tension. All right. T is equal to 1 into 2g by 3, which is equal to k naught into x naught. So x naught is equal to 2g by 3 k naught. All right.
Yes sir.
Okay. Now Now, given the tension, I got the extension. But if I give you the extension, we should also be able to find the tension. How will I find it? K naught X naught. Let's say I've got a block. Spring is like this. There's another block here. This is mass. This is block A and block B. Block A, block B. This is the natural length. All right. Spring constant is K naught. Now, I pull this block B by X naught, X1 or X2. Let's say this is A naught and this is B naught. A naught. Let's say I pull this block A by X1. What is the extension in the spring? Holding this block, I'll pull this block by X1. What is the extension in the spring?
X1.
X1, right. That's it. So what is the force on the spring? Force in tension in the spring? K naught into X1. Right?
Yes,
But
sir.
now I hold this block and pull this by X2. Again, I bring back to the original situation where natural length is L naught, distance between them is natural length, and I hold this block A and move this by X2. What's the extension in the spring?
X2.
Right. What's the tension in the spring?
K naught into X2.
Right. Now I pull both the blocks with X1 and X2. What is the extension in the spring now?
X1 minus X2.
I pull it here, I pull it here. One towards
Sir,
right, one towards left.
X1 plus X2, sir.
X1 plus X2. So what is the tension in the spring? K naught into extension.
Yes, sir.
But what if I do? I move this by X2 and move this by X1. Then what happens?
X1 minus X2, sir.
So K naught into X1 minus X2 is my force. But then tension is the spring. But then is the spring being compressed or elongated? How do I get it? String elongate అయిందా compress అయిందా ఎలా తెలవాలి?
Then distance ని బట్టి తెలుసుకోవచ్చు, sir.
Correct. If X1 is greater than X2, it's elongated. If X1 is less than X2, it's compressed.
Yes, sir.
All right. That's how you can find out. Let's say this 3 centimeters and this 2 centimeters. Natural length 5 centimeters అనుకుంటే ఇది 3 natural length 50 centimeters అనుకుంటే is what 3 centimeters is 2 centimeters అంటే extension is 1 centimeter. But if this is pulled towards left and right, then its extension itself. If both are pushed towards one is B is towards right and A is towards left, compression itself. But if one is to move towards right, both are moved towards right, but with different extensions, different displacements, then I'll have extension or compression depending on whether X1 is greater than X2 or X1 is less than X2. If X1 is equal to X2, what is the extension in the spring?
Normal, sir. Starting into
Natural length, no extension, right?
Yes.
Natural length. Okay. All right. Now, let's say K naught is equal to 200 Newton per meter. This mass is 1 kg. This mass is 2 kg. All right. I pull this with a displacement of 1 centimeter. Holding this one, I pull this with 1 centimeter. I have to find and leave it. So this block is somewhere here. This was the natural end position. From natural end, I have pulled it by 1 centimeter. Or initially, let's say it's X naught. K naught, X naught, 1 kg and 2 kg. I have to find the acceleration of the blocks. So what do I do for the acceleration of the blocks? FBD. For FBD, I need a reference frame. So I choose ground as reference frame. There's no accelerator reference frame here. I mean, there's no lift or elevator or anything like that. There is an accelerator reference frame, but I'm choosing ground to be my reference frame, inertial reference frame. So there's no pseudo force because ground has got no acceleration. That's the inertial reference frame. I'll draw the FBD of 2 kg and 1 kg. 1 kg FBD ఎలా ఉంటుంది? K naught, X naught, 1 kg. 2 kg ఎలా ఉంటుంది? Towards left, K naught, X naught. 2 kg. So acceleration of this one will be k naught x naught by 1. Acceleration of this is k naught x naught by 2. A1, A2. Do you all agree with this? I mean, it's pretty simple, right?
Yes, sir.
Okay. Now, I've got a wedge. On which, let's say this is 30 degrees, 60 degrees, sorry. All right. Spring constant is k naught. Mass of the wedge is m naught. There's another block of mass m naught here. Or let's say mass of the wedge is not given. All right. Now I have to find out the equilibrium extension in the spring. But let's see what is happening first. See, let us understand the scenario. Questions you can frame on your own. Once you understand the complete scenario, any question you can answer easily. Because all the answers you have in front of you, any question framed can be just all you have to do is pick up the answer from the scenario. So let's understand what is happening first. I asked you what is the equilibrium extension in the spring, right? For that, let's understand the scenario. ఇది ఇలా ఉంటే equilibrium extension of the spring అంటే this is in equilibrium. That means this wedge is in equilibrium. Wedge is in equilibrium అంటే that's not moving at rest. All right. Equilibrium could mean two things: at rest or uniform motion. But I'm talking about it when the wedge is at rest. All right. Because if wedge is moving, this will not be in equilibrium anymore. అంటే స్ప్రింగ్ కంప్రెస్ అవుతుంది, ఎలాంగేట్ అవుతుంది, అప్పుడు ఈక్విలిబ్రియం ఉండదు. ఈక్విలిబ్రియం పొజిషన్ ఉంటుంది, బట్ ఈక్విలిబ్రియం మోషన్ ఉండదు. రైట్, సో విల్ నాట్ హ్యావ్ యూనిఫామ్ మోషన్. But for it to have uniform motion, it only means that it's at rest. So wedge is at rest. But why am I talking about compression of the spring or extension of the spring? Because when this block moves down the inclined plane, if I draw the FBD of the wedge, normal force, one normal force is here because of ground. Gravitational force on the wedge is downward. This normal force, because of the block on the wedge, is perpendicular to the wedge this way. Spring forces because of spring over here. Now look at this. I have a component of n, vertical component and horizontal component. This vertical component is counterbalanced by n1. But horizontal component has to be balanced. Otherwise, this wedge will start moving towards left. If there were no spring, this block would come down and the wedge would move towards left.
సార్ యు మీన్ అంటే దాని మీద ఇప్పుడు వెడ్జ్ మీద ఆ బ్లాక్ వెయిట్ ఉంది, ఆ వెయిట్ జారిపోతున్నట్టు ఆ వెయిట్ తగ్గుతుంది కాబట్టి వెనకాలకి వెళ్తుంది అంటున్నారు.
వెయిట్ తగ్గుతలేదు, అది వెయిట్ జారుతుంది కదా. ఆ
యా
జారినప్పుడు నార్మల్ రియాక్షన్ ఉంటుంది కదా మధ్యలో, ఈ రెండింటి మధ్యలో. ఆ నార్మల్ రియాక్షన్ వల్ల నార్మల్ రియాక్షన్ కి కాంపొనెంట్ ఉంది లెఫ్ట్ వర్డ్. నార్మల్ రియాక్షన్ ఇలా ఉంది కదా,
ఎస్ సార్.
దానికి కాంపొనెంట్ ఉంది కదా, లెఫ్ట్ వర్డ్ కాంపొనెంట్ ఉంది కదా, హారిజాంటల్ కాంపొనెంట్ ఉంది. Now that has to be counterbalanced. I said it's an equilibrium, so that has to be counterbalanced. For that to be counterbalanced, my force on the wedge due to spring should be towards right. This is normal component, n component. So spring force should be towards right. For the spring force to be towards right, I should have a compression in the spring. If I have an elongation in the spring force will be towards left. If spring force is towards right, that means there is a compression in the spring. That's why I asked what's a compression in the spring. Students, is it clear? I repeat. Normal reaction between the wedge and the block is in this direction, perpendicular to the wedge. All right, ఆ నార్మల్ రియాక్షన్ ఎంత తర్వాత కనుక్కుందాము. బట్ దెర్ ఇస్ ఎ నార్మల్ రియాక్షన్. దానివల్ల ఒక కాంపోనెంట్ ఉంటుంది, హారిజాంటల్ కాంపోనెంట్, విచ్ ఇస్ n నాట్, సమ్ కాంపోనెంట్ ఉంది, కాంపోనెంట్ కాంపోనెంట్ ఆఫ్ ఎన్ నాట్. అది యాంగిల్స్ కనుక్కుంటే మనం కాంపోనెంట్ రాయొచ్చు, దట్స్ నాట్ ఎ బిగ్ డీల్. బట్ ఎన్ నాట్ కాంపోనెంట్ షుడ్ బి కౌంటర్ బ్యాలెన్స్ బై స్ప్రింగ్ ఫోర్స్. Spring force is towards right, has to be towards right. That means spring has to be compressed. So the question could be, what is the compression in the spring? అది ఇలా ఉందనుకోండి, when I talk of compression or extension in the spring,
Compression only, sir.
ఇక్కడ చూడండి, what is happening? ఈ బ్లాక్ తీసేస్తే నార్మల్ రియాక్షన్ ఇలా ఉంది, రైట్? నార్మల్ రియాక్షన్ వల్ల కాంపోనెంట్, హారిజాంటల్ కాంపోనెంట్ టువర్డ్స్ రైట్ ఉంది. సో స్ప్రింగ్ ఫోర్స్ హ్యాస్ టు బి టువర్డ్స్ లెఫ్ట్. ఫర్ స్ప్రింగ్ ఫోర్స్ టు బి లెఫ్ట్, there has to be an extension in the spring, right? సో ఇక్కడ ఎక్స్టెండ్ అవుతుంది, ఇక్కడ కంప్రెస్ అవుతుంది. లుక్ ఎట్ ద డిఫరెన్స్.
Yes, sir.
Wedge మీద force component towards right ఉంది. That force has to be counterbalanced by the spring, for which the spring has to be stretched. Alright, ఈ నార్మల్ రియాక్షన్ వల్లనే ఎక్స్టెండ్ అవుతుంది, బ్లాక్ టువర్డ్స్ రైట్ మూవ్ అవుతుంది. ఐ మీన్ బ్లాక్ మీద ఫోర్స్ టువర్డ్స్ రైట్ ఉంది, బ్లాక్ మూవ్ అవ్వట్లేదు, బ్లాక్ ఇస్ ఇన్ ఈక్విలిబ్రియం. బ్లాక్ మీద ఫోర్స్ టువర్డ్స్ రైట్ ఉంది, and I said it's in equilibrium. That means spring force has to be towards left. That happens only when there is an extension in the spring. So valid question is, what is the extension in the spring here? Valid question over here is, what is the compression in the spring here? All right, or there could be a question, is the string elongated or compressed? Here elongated, here compressed. So next question, follow-up question would be, what is the compression, what is the elongation? Do you all understand this point? Vignesh,
Yes, sir.
is your doubt cleared?
Yes, sir.
All right, others?
Yes, sir.
Oh, what happened, Ashita? You fine? Is your health okay?
Yes, sir.
Okay. No, I mean, you sound so dull, so I asked you. All right, sure, okay, that's fine. Okay, now let's find out the extension or compression in the spring. ఎలా కనుక్కుంటాను? Ultimately, I want n naught. N naught వచ్చేస్తే నాకు, I take the n naught component equal to compression k naught x naught. Right? Now let's find out n naught. N naught ఎలా కనుక్కోవాలి? ఈ బ్లాక్ మీద n naught ఇలా ఉంటుంది. Its reaction on the wedges, n naught ఇలా, అలా ఇలా. mg is downwards, m naught g. This angle is 60 degrees. So this angle is 60 degrees. So mg cos 60 is equal to n naught, because in this direction it's in equilibrium. There is no motion in this direction at all. Perpendicular. కింద స్లైడ్ అవుతుంది, with g sin theta స్లైడ్ అవుతుంది అది. Right? g sin theta అంటే g root 3 by 2 తో స్లైడ్ అవుతుంది. But perpendicular to the wedge, there is no motion. So I will write n naught minus mg cos 60 equal to 0. So n naught is equal to mg by 2. నాకు n naught వచ్చేసింది. Fine, that's fine. But now I got n naught. I want the horizontal component of n naught. అది ఎంత ఉండాలి? ఇది 60 అంటే ఇది 30, ఇది 60, ఇది 30. So n naught cos 30. n naught cos 30 అంటే mg by 2 cos
Root 3 by 2.
root 3 by 2. This should be equal to k naught into extension or compression. Is it a compression or extension? In this case,
Compression, sir.
compression. So x naught compression is equal to mg root 3 by 4 k naught. Is it okay, students?
Yes, sir.
Yes, sir.
All right. So today you'll have a bit of homework. One is, you understand, you go through whatever you have done. So their homework is AX graph ఒకసారి revise చేసుకోండి. All right, you go to the video or revise, or whatever, if you have written some notes, you revise. Think through AX graph. ఇక్కడ వదిలేస్తే ఎక్కడ అవుతుంది, ఇక్కడ నుంచి వదిలేస్తే ఎక్కడి వరకు స్టాప్ అవుతుంది, సిమెట్రిక్ గా స్టాప్ ఉందా, సిమెట్రిక్ గా స్టాప్ కాదా, రైట్, ప్రొజెక్ట్ చేస్తే ఏమవుతుంది, లెఫ్ట్ వర్డ్ ప్రొజెక్ట్ చేస్తే ఏమవుతుంది, రైట్ వర్డ్ ప్రొజెక్ట్ చేస్తే ఏమవుతుంది, జస్ట్ క్వాలిటేటివ్ డిస్క్రిప్షన్, నో క్వాంటిటేటివ్. క్వాంటిటేటివ్ విల్ డూ ఇట్, ఈక్వేషన్స్ మనం రాద్దాము, బట్ యూ అండర్స్టాండ్ ద క్వాలిటేటివ్ పార్ట్, రీజనింగ్ పార్ట్. ఇలా చేస్తే ఏమవుతుంది, అలా చేస్తే ఏమవుతుంది అని రీజనింగ్ చేయండి మీరు, అదే థింక్ త్రూ, విజువలైజ్ చేయండి. ఇఫ్ యూర్ లెఫ్ట్ విత్ టైమ్, యూ ప్లీజ్ గో త్రూ స్ప్రింగ్స్ ఇన్ యువర్ బుక్. సెంగేజ్ బుక్ ఉంది కదా, దాంట్లో స్ప్రింగ్స్ ఉంది. యూ గో త్రూ ద స్ప్రింగ్స్ అండ్ బీ రెడీ విత్ బేసిక్ అండర్స్టాండింగ్ స్ప్రింగ్స్. స్ప్రింగ్స్ ఎంత చెప్పాను అంత గో త్రూ కావచ్చు, ఆర్ యూ కెన్ ఆల్సో గో అహెడ్ విత్ series and parallel combination of springs. All right, that we'll do tomorrow. First, we'll do graphical analysis of some spring situations. I'll tell you what is the situation we are going to analyze. We are going to analyze a vertically hanging block. Vertically hanging block ఉంది, natural length L naught ఉంది, equilibrium extension X naught ఉంది, మాస్ M naught ఉంది. Now ఇక్కడ నుంచి డిస్ప్లేస్ చేస్తాను నేను పార్టికల్ ని. దీన్ని మనం గ్రాఫికల్ అనాలిసిస్ చేసి we'll do the physical analysis and graphical analysis of this one. It will hardly take 5 to 10 minutes, but it's very important. All right. Sarina students, you remember your homework? One is just revise whatever we have done. All right, compression ఎలా వచ్చింది, extension ఎలా వచ్చింది, tension ఎలా కనుక్కోవాలి, extension, what is the compression extension, x1 x2, x1 greater than x2, x1 less than x2 అని ఒకసారి విజువలైజ్ చేసుకోండి. Then second thing is you revise AX graphs. AX graphs రెండు ఉన్నాయి మనకి. One is ఇలాంటిది ఒకటి, ఇలాంటిది ఒకటి. Revise this one. This one is would be enough. We have done face portrait also for this one. ఇది కనుక్కోండి, ఇది చదువుకోండి ఒకసారి, రివైజ్ చేసుకోండి దిస్ పార్ట్, లెఫ్ట్ వన్. Alright, even if you don't do this one, that's okay, but this is very important for tomorrow. Alright, and then if you still have time left with some time after doing other subjects also, because every subject is important, then you go for spring forces in Cengage. Alright students, we'll stop here. Thank you so much and happy Teachers Day to everyone, each and
Happy
every one of you
Teachers Day,
here.
sir.
Happy
Thank you so much. Thank you so much. Bye everyone.
Bye, sir.
Bye bye.